Assalamualaikum and good day everyone. Welcome back to my class on adaptive control and intelligence system. Today I'm going to talk about another type of adaptive controller which is called Self Tuner. Self Tuner can be a simple controller. For example, you have a PID controller and how that PID controller can be changed to adaptively so that whenever your system parameter changes, the PID controller parameters in PID controller can be updated according to the changes of the parameter. Let's have a look at this plan where the system is described by an ARCS model with parameter of B over A. It's a polynomial, okay? And we have this input of U and output of Y. The objective of this system is actually we want to cancel the uh, steady state error by having the system following the reference that given to the input given to the system. Okay, so the polynomial A and B is described here. Let's say we start with the polynomial A of A is equals to 1 plus A1Z minus 1 plus A2Z minus 2. This is a second order system. And then for the B, we have the polynomial here is actually B1Z minus 1. Okay, so what we want to do is we want to design a controller. So we've talked about PID controller just now, isn't it? So normally for PID controller, the error of the system is actually is an input to the controller. So let me just, before I can describe the design feedback for this controller, let me just give you a brief information on how PID controllers, the basic of PID controller. Let's say we have a system with this, let's say we have a system with input of R, output of Y, and it is actually having a PID controller. So normally PID control will be control with the input of PID control is the error between the reference signal given to the system and the actual response Y that is obtained from the system. Okay, and let's call that output from your PID controller as M. Okay, so what happened is that output M will be given to the system, the transfer function of your system, or maybe in the real application, the controller output M will be given to your actuator. So the actuator will actually move your system to conduct whatever control strategies that are given to the system. Okay, so for PID controller is as simple, the word PID is coming from proportional, derivative, and integral control, isn't it? Proportional, integral, and derivative. That I is actually coming from the word integral, plus the D is actually derivative controller. Okay, so when we talk about P controller, for example, let's have a look at the P controller in the beginning. Okay, so P controller is simply mean that your input and output from your controller, which is M, the output from your controller is proportional to the input to your controller, which is the error of this system. Okay, so if we have that kind of proportionality, what we want to do is actually we want to, let's say I want to remove that proportionality and just have a equality there. So if you want to have equal signal, so you have to be having a constant. So let's have a constant of E. And because this is a P controller, we normally call this constant. We will actually utilize the constant with a subscript of P. So it's a Kp, the constant, the gain that actually given to the system. So if your system is in time domain, then you need to actually take Laplace transformation for it. So it will actually convert from time domain. Let's say it is starting with time domain here. Okay, so if I take Laplace transformation, it will become a ms. Okay, Kp doesn't have any changes because it's a constant. That E signal will be, the error signal will be a Laplace signal in S domain. Okay, so this is for your P controller. So the transfer function of your controller, when we talk about transfer function, normally I will use GC. GC is equals to the output from your controller, okay, divided by input that is given to your controller. Therefore, this is only, now the controller will become just Kp, okay. So your controller is just a gain with the value of from 0 until infinity. Okay, so and this is actually called a proportional controller. Right. So similarly, for your integral controller, so for integral controller, we use I. Okay, so it simply means similarly, the output of your controller is proportional, but not to to the error directly, but to the integral of your error. Okay, let's say it started with let's started with time domain. Okay, so it is proportional to the integral of your the error, integral of your error, right? So to remove the proportionality, again, we're going to introduce the constant ki, or again to the system, and then we take Laplace. All right, if I take Laplace transformation, mt will become ms, that integral et over et dt will become es over s. Okay, so if you take Laplace transformation, okay, from your time domain to your s domain. All right, so then if I want to remove that proportionality, I will actually have that ms is actually equivalent to k, okay, again, all right, whatever gain it is, all right, es over s. All right, since this is integral controller, I'm going to call that gain ki. So then you get your parameter ki. So then if I put this in terms of transfer function, right, you know, transfer function gc from your controller is equivalent to the output from your controller divided by input given to your controller. So that will leave me with ki over s. So this is actually the controller for integral controller. All right, so that's integral controller. What about derivative controller? All right, derivative is denote what with d. Okay, similarly, the error is actually proportional. Okay, sorry, the output, not the error. The output mt is proportional to the error et, but not really the error itself, but the derivative of the error dt. Let me just rewrite that nicely. Okay, so it is proportional to the derivative of error over dt. Okay, so this is in time domain. So if I take Laplace transformation, mt will become ms. All right, and that dt, de over dt will become, okay, s multiplied by es. Okay, so if I take Laplace transformation by considering all the initial conditions are 0, so this is what we're going to get. Okay, so to remove that, to remove the Laplace, to convert it, to remove the proportionality, I will actually have ms equals to some constant, okay, multiplied by s es. Okay, so what is that constant? So it's a gain with the I'm just going to have a subscript d, so that we can actually differentiate between proportional controller, integral controller, and derivative controller. So uh, again, so if I write the controller transfer function gc is equals to the output divided by the input of the controller, and that will leave me with kd multiplied by s. So this is your derivative controller for PID. All right, so simply if I want to have a PID, I'll just add all these things together. All right, so not in this case for derivation, I will show it one by one. I've shown it one by one, but then for the PID controller, it is actually a combination of all these three. Okay, so if we say, what is a PID controller? PID controller is actually, you are having your error, sorry, you are having your output of your controller M proportional to, first, it is proportional to the error, okay, plus it's a proportional to the integral of your error. At the same time, it is with okay, proportional to the integral of your error with dt. Oops, with dt, yeah. And then plus it is also proportional to your derivative of your d of your error over dt. Okay, so when it is actually proportional to all these three, you can repeat the same procedure like what we have done in the beginning. Okay, but I can just simply summarize that it is equivalent to kp, okay, multiplied by your error es. Let's say we just immediately take Laplace transformation and do the conversion straight away. Okay, kp es plus ki es over s plus kd s es. Okay, then with that, if I collect all the error together, and I will have the transfer function of my system, gc is equals to ms over es, because output over input. Okay, that will be equivalent to we have kp plus ki over s plus kd over kds. Okay, so that is your PID controller. Therefore, when you have this kind of strategy with the PID controller, what it simply means that you have your input R, okay, and your transfer function GC here will be all those values. You have KP plus KI over S plus KDS. So that is your PID controller here. Okay, so this is the parameter of PID controller that you're going to put in your transfer function of your controller. Okay, and then that output M will be given to your actuator, and then it will be given to your system. All right, but normally for to make it simple, okay, we just put it directly to our system. Okay, but you know that in reality, when you want to implement this controller, it will be given to the actuator of your system. All right, so in case of simulation, we're going to assume that the actuator is having transfer function of 1, or the actuator is actually part of your system. Okay, so error from PID is actually always the input of PID is always the error from the reference signal with your actual output Y here. Okay, so this is a basic of PID control. So, but what we want to do is actually for this adaptive control is that you know that the transfer function of your system is always changing. Okay, you always have to model the transfer function of your system. The parameter of your system always changing. Therefore, the value of your PID controller need to be updated all the time. Okay, so in terms of a normal system which doesn't have changes of parameter, you can design your PID controller and then with the same value, it can control your system without having any reduction of performance of your controller. But when the moment your system change in its parameter, okay, then your PID controller performance will reduce. So what you need to do is when the parameter of your system, for example, the value of A, B of your system is changing, your controller also need to be updated. Means to say you want to change the value of KP, KI, and also KD, the gain of your PID control. So how can we do that? All right, so what I'm going to show you next is the derivation on how we can convert from the PID into the becoming a self tuner. So we have two equations. We have our equation from the original PID in Laplace domain, and then we have the equation of G over F in zero or the whole that we want to design. Okay, so how to do that? Right, so if you look at your equation the earlier from your PID, US is equals to KP over plus KI over S plus KD over KDS. Okay, so if I want to actually simplify, this is of course multiplied with your input error. So this is the whole thing is multiplied with error. Okay, so I can just bring that error to the other side. Okay, so just have this is actually divide by error. Okay, so that is your transfer function GC. Okay, output over input. Right, so what I'm going to do is I'm going to multiply all of them with S so that the denominator is going to be just S. So I'm going to have KPS plus KI plus KD s squared. Okay, the whole thing is divided by s. Okay, then I need to actually compare this with my proposed transfer function. The proposed transfer function for my controller in zero or the whole is that u z minus 1 over e z minus 1 is equals to, this is what are we proposing just now, which is g naught plus g1 z minus 1 plus g2 z minus 2. So you don't need to find the model order for your G and for your F, because for PID self tuner, we're going to fix it as this. Okay, so you cannot have higher order. All right, and then similarly for your F, a polynomial F is going to be 1 minus F1 Z minus 1. So you might ask me, can we have the value of it's becoming 1 plus f1 z minus 1? In this case, the answer is no, because we're going to use the simplification of s is equivalent to 1 minus z minus 1. Okay, in this case, I don't even need to find the value of f, okay, because f1 I will give it a value of 1. Okay, so in this case, it means to say, if you use 1 plus, so means your value of f1 will be negative 1. So you're still going to have 1 minus 1 minus 1 multiplied by z minus 1. So it simply means that this is going to be just like that. So you don't even need to find the value of f1. Okay, so because we want to have only 3 unknown, because you have g0, g1 and g2, the unknown to your controller. Because for the one that you want to compare with your PID, you also have 3 unknown, which is KP, KI and KD. All right, so when you do the comparison, you can convert it and then you can actually find the solution. Okay, so what I'm going to do then, I'm going to use substitution. I'm going to use approximation of S is equivalent to 1 minus Z minus 1. Okay, so either I substitute the value of S in this equation, okay, substitute S, or I can substitute here the 1 minus Z minus 1 into this equation. So either or, okay, all right, so it's up to you which one you want to do, right? So in this case, maybe I'm going to do it by substituting it into this value KPS and all, right? So from the PID controller, okay, so we have KPS, right? KPS, so S will be 1 minus Z minus 1. So now we are converting it, we're going to convert it into 0 or the whole, okay, plus KI, okay, plus KD with 1 minus Z minus 1 square. Okay, can you see that? Let me just bring it to this slightly. Okay. Oops. The whole thing squared, because you have KD as squared, all right? So 1 minus Z minus 1 also need to be squared, all right? And the denominator will be divided by 1, divided by S, so it simply become 1 minus Z minus 1, okay? So if you look at the equation that you want to compare, it's already, the denominator is already tally, isn't it, between one another. So you don't have to compare the denominator anymore. You just need to compare the numerator of your equation and equate them so that you will actually solve this problem. So that's what we're going to do. So we want to look at the left hand side will be G naught plus G1 Z minus 1 plus G2 Z minus 2. Then it will be equivalent. Okay, so because we want to find out this, isn't it? So I'm going to equate that together. Okay, so the denominator is already the same, so I'm going to ignore that. I'm just going to compare with the denominator with the numerator. So, sorry, I'm going to compare the numerator only, not the denominator. So on the other side, I will have Kp multiplied by 1 minus Z minus 1. That will give me Kp minus Kp Z minus 1 plus Ki. Okay, KD multiplied by 1 minus Z minus 1 squared, you need to actually expand that. Okay, if I expand 1 minus z minus 1 square, that will become what? It will become, of course, 1 minus z minus 1 multiplied by 1 minus z minus 1. Okay, that will become 1 minus z minus 1 plus, okay, so you have another minus, right? Z minus 1, okay, and then it become plus z minus 2. All right, so because you have z minus 1 multiplied by another z minus 1, it becomes z minus 2. The negative and negative become positive, and it becomes z minus 2. That will give me 1 minus 2 z minus 1 plus z minus 2 for the square of 1 minus z minus 1. So that will be multiplied with my value of kd. Okay, so then it will be a bit long, isn't it? So if I put here plus my kd will become kd multiplied by this square equation, 1 minus 2 z minus 1 plus z minus 2. All right, so that's how you do it. Okay, so let me just erase this. Okay, so if I further expand that, you're going to have g naught plus, similarly for the first part, it will be the same, isn't it? Okay, then I'm going to have this equals to kp minus kp z minus 1 plus I plus kd minus 2 kd z minus 1 plus kd z minus 2. So what we can do later on, we can actually compare the coefficient from the left hand side and right hand side. Okay, so we do that. Let's compare the coefficient of z to the power of 0. So I'm going to have one side is g naught, the other side will have kp plus ki plus kd. Okay, so that's one equation that you have. So if you compare the value of your z minus 1, okay, on the one side you're going to have g1 equals to, on the other side you're going to have negative kp, all right, negative kp minus 2 kd. Okay, so you don't have any more z minus 1, right, on the other side. So that's for your g1. Okay, then compare the coefficient of z minus 2. On one side you have g2, on the other side you're going to have just, sorry, I forgot, this one is kd just now, isn't it? On the other side you're going to have z minus 2 is only your kd, isn't it? Is that right? Okay. Okay, so you have these three unknowns, and then you're going to actually have three equations, okay, where your g naught is equivalent to the value of your kp plus ki plus kd, and g1 is equals to negative kp plus minus 2 kd, and g2 is equals to your kd. Okay, so you can then use this to find out again what is the value of kp, ki, kd in as a function of G1, G naught, G1, and G2. Okay, so that can be done if we do the different substitution. We do it the other way around. So there are two ways that you can do it. So this is the first way. You get that equation. Okay, the second way, if I, instead of substituting S into the PID equation, I can substitute 1 minus Z minus 1 and make this equivalent to S. Okay, we can do that as well. All right, so let's try that as well. Okay, so that you have both ideas on how to do it. Okay, remember again, so this is the first method. The second way is, if I, instead of have that, I can substitute S is equals to 1 minus Z minus 1. Therefore, Z minus 1 is equals to, right, 1 minus S, isn't it? Okay, so instead of using S to substitute, I'm going to substitute Z minus 1 into the equation of your G naught. So if you look at the transfer function of controller again just now, it is G naught plus G1 Z minus 1 plus G2 Z minus 2 divided by 1 minus Z minus 1. Okay, so what I'm going to do then, this is going to be substituting that into this equation. I'm going to have G naught plus G1, Z minus 1 will be 1 minus S, right? Okay, then plus G2, Z minus 2. Okay, Z minus 2, it means to say I have Z minus 1 square, isn't it? All right, then I become Z minus 2. So that is the same as having 1 minus S square. Okay, so can we do that? 1 minus S square. Okay, so yeah, we can do that, right? So this is actually 1 minus S square. All right, and the denominator, since S is being used as 1 minus Z minus 1, so the denominator is quickly becoming just S. So this is why we have that polynomial F as a value of 1 minus Z minus 1 just now. All right, okay, then let's expand this. Then I have G naught plus G1. Let me just expand that. G1 minus G1S plus, okay, for your 1 minus S squared. Okay, so if you expand it, it will become 1 minus 2S plus S squared, isn't it? Okay, if I expand that, okay, so then I multiply that with G1, G2, so I will get G2 minus 2, sorry, G2 minus 2 G2S plus G2S squared. Okay, so that what we have. Okay, so and then the same way the denominator is remaining as S. So then I can compare this with the PID value, right? So if you look at the PID just now, it was what? It was KPS plus KI plus KDS. KDS squared divided by S, isn't it? So that was the value just now. So we can actually compare this with the value that we have here. Compare this with the equation that we have derived earlier just now. Okay. It's too big, so maybe make it smaller. It's not very nice, but it's there. Okay. So we can do that. All right, since the denominator is already the same, so what we can do is then just compare the numerator. All right, so if I can compare the numerator, I will compare the coefficient of S0 first. So if you look at the coefficient of S0, on one side, you're going to have Ki. On the other side, you have what? What do you have? For S0, you have G naught plus G1 plus G2. Okay, so that is for coefficient of S0. What about coefficient of S1? Okay, on one side you have Kp. Okay, what is Kp then? Kp is equals to, look at the other side, what do you have? You have negative G1, okay, for to the power multiplied with S, minus 2 G2, okay, multiplied by S. All right, so that's what you have for your Kp. And then if you look at the coefficient of S2, you're going to have, on one side, you're going to have Kd. On the other side, you're going to have G2. All right, so this is tally with the one that we have developed earlier. We know that Kd is already equals to G2. Okay, so this is another substitution or another way that we can do it. So either you substitute S into your polynomial G over F, or you substitute 1 minus Z minus 1 into your PID controller, then you get these two types of relationship, right? So we can use both of them. We can use either or. So it's up to you which one you want to use. Okay, let's have a look again to the problem that we have. All right. Okay, so if you look again at the design of your controller just now, so you can have, by doing this substitution, you can do both, isn't it? Either you have this as your equation just now, or you have this as your based on your substitution. Okay, so whichever you want to use for your controller, then you can put this into your transfer function of your controller, that like what we have here. Okay, so then how can we actually look further into this, right? So if you look at your controller, you have to look at the overall transfer function of the closed loop system equation, because your controller is having G over F. At the same time, you have your transfer function of your system, which is B over A, Z minus K B over A. So can we get our closed loop system equation based on this? Because we have our objective, isn't it? The objective is to have the steady state error of 0, isn't it? So how can we do that? All right, so if you look at your closed loop system equation, I already have it summarized here, but really how do I get that is by just doing the closed loop. So let's have a look at the how we do it in terms of a closed loop system equation. Okay, so if you go back to the notes, so maybe if I want to write in terms of closed loop system equation, so the initial equation was having this G over F here, and then let's say our transfer function is Z minus K B over A, and then we have our closed loop system. All right, so what we can do then is actually we want to have a closed loop system equation, of course. So how to do that? You know y is equals to G over F multiplied by this, because it's in series. So G over F need to be multiplied with your transfer function GS here. So I'm going to have that as a G Z minus K B G over F multiplied by A. Okay, that of course multiplied by your signal here is your error signal there. Okay, so what to do then is actually to find out what is your signal error, isn't it? Your error is equals to your R minus Y. Okay, so then we're going to substitute that into this equation. So I have Y is equals to Z minus K B G divided by F A multiplied by R, okay, or minus Y. So we have substituted E with the relationship of R minus Y. But you can see that you now have two terms of Y. So we need to actually maybe expand this and then factorize it and then collect all the Y together. Okay, so I will multiply my F A with Y. So that will be Z minus K B G R, also minus Z minus K B G Y. Oops, that's G. Sorry. Okay, so then I will collect all the Y together. So bring that Z minus K B G Y into the other side. So I will have Y. Now I will have both, isn't it? F A plus B G. Sorry, Z minus K B G. Okay, that is equivalent to Z minus K B G R. Okay, so then what we do with this is, of course, we want to know Y. Y is equals to Z minus K B G divided by your F A plus Z minus K B G multiplied by R. Okay, so let's check that. Is that correct or not? Okay. All right, so that's how it is. Okay, so then this is your closed loop system equation for the overall system, including the controller that you have developed. Okay, so then what do you need to do? You need to actually substitute the polynomial A and B into this equation, plus your polynomial G and F into the equation. Then you will get the transfer function that I have actually shown you earlier. So let's do that. Let's copy this and then bring it to our slide. Okay, so if you look at again, so this is how I got it. So how do I got it? I got it from that activities just now that way. That's what we've done, okay? All right, so that is actually coming from the equation that we have earlier. All right, we derived it earlier. So you have your y and your r here, right? Okay, so you have your y and your r, and then that polynomial is actually, I already put the polynomial b. If you have delay z minus k, you're going to put that, but in this case just now we look at the system, it only have b minus b1 z minus 1, isn't it? So that's your polynomial b, okay, and this is your polynomial g. All right, okay, at the bottom here I have one minus I have actually expand the value from f multiplied by a, okay, because I know my, remember for the polynomial f we straight away use 1 minus z minus 1, isn't it? Okay, so that need to be multiplied with your polynomial a, and then you need to add with the polynomial b multiplied by g. So that will give you this huge equation that I've shown you in this slide here. All right, then similarly what you want to do is you want to actually assign this closed loop system equation, the denominator of this the denominator of this closed loop system equation is your characteristic equation, isn't it? So that characteristic equation is need to, in order to make it stable, you can use pole assignment to assign it to a stable pole. So in this case, I'm going to assign it with this pole here, which is 1 plus t1 z minus 1 plus t2 z minus 2. So these t1 and t2 are my stable poles, okay? So if we can put that into our closed loop system equation, you can see that the denominator is straight away converted into our stable poles. But in order to do that, we need to equate the two denominator together, isn't it? So if I take that denominator here, okay, oops. So I take that closed loop system equation, the original denominator of my system, and then I actually convert it with that, right? So I can just equate them, and by doing that I will get the value or the polynomial, oh sorry, the parameter of my g naught, g1 and g2. How is that so? Let's have a look. Okay, let's do that. Okay, in terms of derivation. Okay, so if we can look again at this closed loop system equation that we have, and then we need to substitute all the polynomial into this equation, and then try to equate with the stable poles that we would like to design. Okay, let's have a look at how to do that. All right, so I have for my y, okay, I can start right, y is equals to, let's say we have y over r straight away. Okay, so we have for b is b1 z minus 1. Okay, and then you have for your g, it's a g naught plus g1 z minus 1 plus g2 z minus 2. Okay, that's for your b. And then divide by your f, you're going to have 1 minus f1 z. No, you don't have f1. Just straight away have, oops, 1 minus z minus 1. Okay, that's for your f, polynomial f, multiplied by your polynomial a, which is a1 z minus 1 plus, it's a second order here you're using just now, isn't it? So, sorry, polynomial a1 a naught. We have a naught, I forgot, 1 plus. Okay, plus again your equation that you have on top here, isn't it? Similar for this. Okay, so plus that, so that's going to be your very long denominator that you have for your system. Okay, so that denominator need to be equate with your stable poles. So because your denominator here is your characteristic equation. So these are your characteristic equation. Okay, so you need to actually equate that with your stable poles. All right, so if I can just summarize it or factorize it with the value of z minus 1 collected together, z minus 2 collected together. So how is that going to look? Okay, so let's have a look. It's going to be 1 minus, sorry, 1 plus a1 z minus 1 plus a2 z minus 2, okay, minus z minus 1 minus a2 a1. Okay, plus, let me just write bottom here. I'm gonna have b1 z b1 g note freeway plus b1 g1 plus b1 g2 z minus 3. Okay, so then this equation is equate to be equals to your stable poles equation, which is 1 plus t1 z minus 1 plus t2 z minus 2. I can stop there, or I can, if I decided to have more poles, I want to have 3 poles rather than 2 poles, I can just have t3, isn't it? Z minus 3. I will explain about that later on, okay, in the class. So, but in this case, I'm just going to use 2 poles, all right? So it's just like that, okay? So if we equate this, I can further summarize the left-hand side equation by collecting all the z minus 1 together. So I'm going to have 1 plus, sorry, 1 plus, I'm going to have a1. For z minus 1, I'll have a1, and then have minus 1, okay, plus b1 g naught. Okay, that whole lot is z minus 1. Okay, then I have plus, for z minus 2, I will have a2 minus a1 plus b1 g1. Okay, so that's for z minus 2. And then I have for z minus 3, I will have minus a2 plus b1 g2 z minus 3. Okay, and of course these need to be equated with 1 plus t1 z minus 1 plus t2 z minus 2. Okay, so if we want to do the equating, so what do is we compare the coefficient of z minus 1, z minus 2, and z minus 3. Okay, so if we go for the first one, z minus 1, on the left hand side I will have a1 minus 1 plus b1 g naught. So that is equivalent to my T1. Okay, so then we want to know G naught, isn't it? I can straight away write from this equation G naught is equals to, so let's have T1 plus 1 minus A1, isn't it? Divided by B1. So that's what you have when you have your G naught in terms of your stable poles and also in terms of the parameter of your system. Okay, so your controller. Okay, then again we're going to do for Z minus 2. So for Z minus 2, I will have A2 minus A1 plus B1 G1. So from this part here, okay, that equals to my T2 from this part here. I'm just comparing coefficients, right? So then I will write in terms of G1 because I want to know the transfer function of my controller. G1 is equals to T2. Okay, then we minus and maybe we plus first with A1 and then minus A2 divided by B1. So that's your G1 in terms of your parameters and stable poles. Okay, lastly we're going to do is for your Z minus 3 by comparing coefficient. Okay, you only have Z minus 3 on your left hand side but not on your right hand side, isn't it? So on your left hand side you have this value here, which is minus A2 plus B1 G2. Okay, on the right hand side you have it 0. You don't have Z minus 3. If you have Z minus 3, then you're going to put here. Okay, the polynomial means, let's say you have third poles. Okay, then you're going to put here. So from here I'm going to have G2 is equals to A2 divided by B1 straight away. So these are the values of your controllers in terms of G0, G1 and G2. Okay, so we can actually summarize this like what you have in the slide. Okay, so let's have a look at the slide again. So these are the values that you have for your G0, G1, G2, like what I have derived. I come to notice there's something slightly a bit wrong just now when I do my derivation. On your slide, I put here minus is supposed to be plus. Can you edit that from your slide? That is supposed to be plus, okay? So rather than minus, okay? So then when you do your comparison, okay, then you get this parameter for your G0, G1, and G2. Okay, and then what you need to do is for your steady state error, okay, for your steady state error, just need to compare the yt over rt or yz minus divided by r need to be equals to 1 so that your steady state error is 0. Okay, so go back to your closed loop system equation. Okay, or you know already when you want to evaluate steady state error, z must be equals to 1. Okay, and then equate that whole equation, your closed loop system equation, into 1. Okay, so let's have a look at that. So we don't have it, so maybe I will put that in the next slide. Okay, so I can take the whole lot here. Okay, then that will actually make it y, oops, make it your y over r equals to 1. Okay, and you have all the z into the polynomial equate it with 1. Okay, so that will be able to solve your problem as well. All right, to make sure your system is having steady state error of 0. Okay, all right, so again, so what you do is you have your plant model. All right, then you have your transfer function for your polynomial a and b. Okay, and then you know that your objective is actually to design a system so that the dynamic of your system is governed with the stable poles. All right, so we've done that. Okay, and then you need to actually have your steady state error become 0, where your system, your output response is following the reference that given to your system. And these are the way we design it just now according to our controller that we have designed it earlier. Okay, then all the parameters that we have actually derived from our controller equation. Okay, so basically what you do when you are going to actually design the system to actually to design to write the algorithm in your MATLAB, for example, what you do is actually you're going to conduct your least squared estimation or recursive least squared estimation from your plan. All right, once the moment you have actually conduct the least square estimation, you will get the parameter a and b from your system. Okay, from the parameter a and b, you're going to substitute into your design rules so that you will have the parameter of your controller G0, G1, and G2 the way that I have derived earlier in this session just now. Okay, so substitute that. From there you can substitute into your output control U signal. Okay, and then you can generate the output control U, and that output control U will be given to your system or your actuator in real system through your data acquisition system. You're going to have it as an output, and then that output will be given to the actuator and given to your actual system, okay, in terms of whatever value it is. Okay, so this can then be repeated. So as long as your system parameter of your system changes, the moment you have your recursive least squared to detect these changes, it will immediately update your system all the time. Okay, you update your controller all the time. Okay, so that is how you do your PID controller. I will show you an example of how to solve PID controller using actual values, okay, actual system in the next video. Thank you very much.